pleased to kick off. Yeah, I'm very, very pleased to kick off our monthly Udall Udall Center's talks. I think most of the people involved know we received our notice of award on Monday, so we're actually officially in business now, which is great. I want to thank everyone who participated in the application. This was a real team effort and with a very, very nice outcome. And so thanks to all of you. Our first speaker for this session is Dan Leventhal, Department of Neurology and BME, and at the VA Ann Arbor Healthcare System. Dan is an electrophysiologist doing sort of behavioral work and a movement disorder neurologist. And he's going to talk today about actually work that he's done that has been at least partially funded by our Parkinson's Foundation Research Center of Excellence, which is strongly relevant to the work in the Udall Center as well. So Dan, go ahead.
Okay, yes, thanks Roger for the introduction. No disclosure. So there's sort of, in my rat and mouse lab, there's sort of three things that we are working on. So one is this little video on the left of rats doing things with their fingers and trying to model the impairments that humans have with manual dexterity and Parkinson's disease. The second project is actually the focus of the Parkinson Center of Excellence, and that is trying to understand the integrative role of the motor thalamus, this chunk of brain here that lies between the basal ganglia and the cortex. And then the last project is a project with Bill Dower looking at dystonia models. But what I'm going to talk about today is this work on the left that was mostly done by Alex Bova, who recently graduated from my lab. So the punchline first, so we sort of know that dopamine makes people move faster, stronger, more frequently, which often gets referred to as more vigorously, which is sort of intentionally vague. But what I'm going to try to convince you of is that at least in our rat model, dopamine also has a role in regulating coordination across joints, multi-joint movement. And that one way to potentially link these things together is through reinforcement learning models, as everyone in the biopsychology world will be familiar with. And then one of the really surprising things that we found is that when we did our manipulations to these rats is that once you had this sort of dopamine-induced abnormal movements, you could make the rats ping pong back and forth between different movement patterns, depending on what you were doing to dopamine in their brain. I'll show you what I mean by that. And then the last bit is a bit that we've been working on with Christian Burgess's lab and actually measuring dopamine transients as mice engage in a dexterous task. And it turns out that there is very precisely timed dopamine signaling during that. So in the interest of time, I'm going to sort of skip through this. This is a video of someone with Parkinson's disease. She has a rest tremor and all the sort of typical features of Parkinson's. And this is a former patient of mine. And the point I'm trying to make here is that people at baseline with Parkinson's, they move slowly, they don't move big enough. But it's not just that she doesn't move big enough. There are progressive changes in the way she moves. The tapping becomes not just slower, but a little bit irregular. And when you give her levodopa and you fill up the dopamine tank, now she moves pretty quickly. Her face is more expressive, and there's less irregularity in the finger tapping. So dopamine pretty clearly makes people move bigger and faster and more frequently. But there are other problems. So kind of interestingly, I canvassed the movement disorders group to see if anyone had a video of a Parkinson's patient struggling with something that required manual dexterity, and no one had one, even though we sort of all see patients who sort of look like they're moving okay, but have trouble with things like buttoning and tying shoelaces. So yeah, it's not just that this man's fingers are slowed down 2x and but still fastening buttons. There's an actual problem with manipulating small objects. So I'm going to take a slight detour, talk about dopamine as a learning signal. So this is the psychologist version of dopamine, not the movement disorder neurologist version of dopamine. So the idea here is that you have a Pavlov's dog type experiment where the subject gets some sort of reward. In this case, it's going to be juice, and there'll be some cue that predicts when the reward is coming. So Wolfram Schultz, in what's now really classic work, showed that if you record from dopamine neurons, a lot of the dopamine neurons will start firing more frequently when an unexpected reward comes.
So Dan, there's something over your slide there. Looks like some of your files there, yeah.
Yeah, I was copying something over, so it must have popped when I pasted it. So dopamine neurons fire more when something unexpectedly good happens. And if you can predict when something good is going to happen, the dopamine neurons don't care anymore. So in this case, a cue perfectly predicts when the reward is going to happen. And now the dopamine neuron fires more when the cue comes because that's unexpected. But it just keeps on trucking when the reward comes because that's totally anticipated now. And you can do sort of the opposite thing where you present the cue that was going to signal the reward, and then you fail to deliver the reward, and you get a dip in firing. And this is more or less correct, although there are a lot of details and nuance to it to sort of get everything to fit together. But the basic idea is that dopamine is signaling a reward prediction error, and that your brain can use that signal to say, hey, something better than expected just happened. I should do whatever led up to that again. And if that keeps happening over and over again, you really reinforce that behavior. And if you get a dopamine dip that says, you know what, that was kind of disappointing. Whatever you just did wasn't all that great. And so you are less likely to perform that behavior, and certainly less likely to perform it with a lot of energy. So this is some experiments from when I was a postdoc. The main point I want to make here is that we have rats doing a behavior. The behavior is not super important right now. The point is the rats got an infusion of a dopamine blocking agent into their striatum. And they, for each of the test sessions, labeled 1 through 5 here. And the point is that the performance is pretty normal on day 1, right? Let's just ignore what the measures are for now because it's not super critical. But over time, performance gets worse and worse. And so that fits with this idea of dopamine being a learning signal and not just being a fuel tank where you tank it up and people move fast and it gets low and people move slowly. So you might ask, well, that's in that case, the rats were behaving, trying to get a reward, a sugar pellet. Can you apply this to things like motor learning? So this is an experiment done in Jesse Goldberg's lab at Cornell, and they have songbirds. So songbird's a nice model system because songbirds have very stereotyped motor behavior that they will perform over and over and over again. And they have basal ganglia dopamine systems that are kind of sort of similar to mammalian systems. And so what Jesse did, actually what Vikram Gadekar did in Jesse's lab, is they have the songbird playing, singing its song. And then on half of the times that the songbird sings, they distort it. They play this audio feedback that screws up the song. And what they find is that at the time that the distorted syllable happens, the songbird's dopamine neurons fire more if the song is not distorted. So the songbird presumably is saying, hey, I got that one right. And if they do distort the song, they see a dip in dopamine neuron activity. And the idea here is that it's not just working for extrinsic reward. There's an intrinsic, gee, I did that right kind of signal that dopamine fires for, and that signal might be used for motor learning, independently of working for fruit juice or whatever the reward might be. So the idea here basically is, let's take a simple, relatively simple task, or at least a straightforward task like shooting a basketball. It's super complicated in terms of what you have to do it right, but the objective is very simple. So Steph Curry shoots a basketball and shoots a basketball and shoots a basketball, and he's really, really good at it. And you might think that every time the ball goes through the basket, or maybe he's so good that he just knows when he lets it go that he did that one well. He gets a little pulse of dopamine in his brain and says, hey, Steph, do it that way again. On the other hand, if you're Nick Young and you shoot and you're pretty confident and then the ball rims out, you might get a little dopamine dip, so you didn't quite do it right that time. And so the question is this type of mechanism at play in rats that we can manipulate, but more importantly in Parkinson's patients? So we have these two not necessarily mutually exclusive ideas that dopamine regulates the vigor of the movement you're doing now. And this is what we see in Parkinson's patients. You give them levodopa, they move faster, the levodopa wears off, they move slower, you give them more levodopa, they move faster again. And the alternative is that dopamine serves as a learning signal that you're using to determine how you're going to move later on. And the question we're going after here, especially with respect to these dexterous skills, not just rats pressing levers or moving left or right, how do these vigor and learning models relate to each other? So if you're going to address this question, the first thing you need is an animal model that can do something with their fingers that requires a lot of coordination, and that is a little bit, but not too difficult for them. The skilled reaching task was developed by Ian Wishaw back in the 80s, and actually there are versions of this going back to the 50s. And it turns out that if you put a barrier up, rats and mice will learn to reach for something like a sugar pellet, and they'll get better at it over 3 or 4 days, maybe 10 days. And they look a lot like humans when they do it. Not only do they look a lot like healthy humans, but if you do something like kill dopamine neurons in the rat, it'll look like a human with Parkinson's. If you lesion motor cortex, they look like humans with strokes. So it's probably a reasonably good model of a dexterous skill in humans. The problem with this task that we ran into when we started to implement it is that this task is a whole lot of work. To get a rat to do 20-ish trials, the experimenter has to take a sugar pellet, stick it on there. Then you have to make some judgment about how the rat's moving, but you don't really know exactly quantitatively how the rat's movements have changed. So one of the first things we did in the lab is we invented this skilled reaching chamber. So the rat can request a sugar pellet. When the rat requests a sugar pellet, this arm in the middle here comes up. We have mirrors on the sides, and what that does is it allows us to record multiple angles and reconstruct what the paw is doing in 3 dimensions perfectly. Well, not perfectly, but reconstruct what the paw is doing in 3 dimensions well enough. And it lets us train a bunch of rats and test a whole bunch of rats simultaneously. So we have 4 of these boxes downstairs, and you can really power through this pretty quickly now. So this is just what the chamber looks like in overview. So there's a photo beam at the back of the chamber. The rat runs to the back of the chamber, which is basically the rat requesting a sugar pellet. The rat runs back to the front of the chamber. There should be a pellet there now. It can reach for it, grasp it, and then it can repeat. And we can record really, really high speed, high resolution video because we have this fancy frame grabber card that lets us do real time calculations on the images. And so we can tell when the rat actually breaches the reaching slot. We're getting video at 300 frames per second at better than high def. So we have really nice images of this. And then what we need on top of the task is we need a way to manipulate dopamine. So an obvious way to do it is to use toxins, but that makes it difficult to sort of tease out the kinds of questions we're going after, because once you've squirted the toxin in, it's permanent, or even squirting drugs in over and over again. So we used an optogenetic technique, and the way the genetics and the viral constructs and everything work are not super important. The main point is that this arch construct is an inhibitory opsin, and when you shine green light on it, it turns off neurons. CHR2 is channel rhodopsin. That's a cationic channel, and when you shine blue light on it, it tends to activate neurons. And then this purple EYFP is a control construct that doesn't do anything to neurons. And we can implant the rats with an optical fiber and attach them to a patch cable and shine light into their brain. And we can turn their dopamine neurons off or on at specific moments while they're doing this task. So in the first set of experiments I'm going to show you, as soon as the rat requests a pellet, the laser comes on. And then shortly after the rat completes its reach, the laser turns off. And this is Alex's paradigm. So the main thing I want you to focus on is out here. These experiments are going to be 10 days, once the rat knows what it's doing, 10 days of stimulating the rat every time it goes to reach, and then 10 days of turning the laser off. All right, and here's what we found. This is just looking at the success rate. How good are the rats at grasping the pellet? So one is their baseline. As the rats go through this paradigm where they're getting dopamine neuron stimulation every single time they reach, they get worse and worse at the task. When you turn it off, they get better and better at the task, and they get better pretty quickly. And if you look within individual sessions, so here the blue is the stimulated rats, the pinkish purple is the control rats that had the control construct injected. You can see that the success rates gradually decline for the stimulated rats. And then they gradually but fairly quickly come back to normal when you turn the laser off. And it turns out that you have to stimulate while the rats are reaching for this to work. So if you switch the paradigm and you only stimulate when the rats are not reaching, nothing happens. So here the purple is rats stimulated between reaches, blue is stimulated during reaches. And you see that the rats stimulated for the same amount of time, but only when they're not reaching, their performance doesn't change. So at the very least, we can say that dopamine, at least in this artificial situation, has something to do with learning dexterous skills, or certainly adapting dexterous skills, because we can gradually change the way that their forelimbs work by repeatedly stimulating dopamine neurons, but it only works if you time it when they're actually reaching.
Dan, can I ask a technical question though?
Yeah.
What were your stimulation parameters?
So the stimulation parameters
laser
were
LED, and what do you know about the amount of dopamine you're dumping relative to
so
regular levels?
yeah, so the stimulation parameters were, I would say, moderately high, comparable to what other people have used, but probably artificially high. So it's 20 milliwatts at the fiber tip and 20 hertz stimulation. I don't know what's happening to the dopamine levels. So other people that have used similar stimulation parameters, I would say these are higher than when people have tried to match to natural phasic dopamine release, but I don't know exactly how high they are. And we're trying to measure that with D-Light now, to figure out exactly how high we're going.
Thanks.
Yeah, I'll come back to that later. So the next question we wanted to address is, well, okay, so the rats are jacked up at this task. They're having problems with it, but why are they having problems with it? What exactly is changing about the way that the rats reach? So the baseline reach is shown here on the left. On the right, you can see that the rat is really not reaching as far as it was before. It's making these sort of truncated reaches, which actually rather surprised us. We thought that they would sort of hulk up and try to smash the pellet when we did the dopamine neuron stimulation. But they actually wound up with these sort of short truncated reaches. And to quantify that, we use Deep Lab Cut, which is a machine learning algorithm for tracking animal poses. The basic idea of it is you take a bunch of video frames of your animal or your human or whatever doing whatever task you're interested in. You label a couple hundred of those frames, you feed it into the computer algorithm. The computer learns what you're looking for, and then you run your videos through the algorithm. And the computer will tell you where, for example, each individual digit is. Then because of the mirrors and because we can calibrate the geometry of the mirrors with respect to the direct camera view, we can back out where the paws are in 3 dimensions. And then we can start analyzing things in a somewhat more automated way. So it's been known for well described for a long time that once rats or mice learn this task, they tend to have a very stereotyped reaching pattern where they'll orient themselves to the pellet and then go through a sequence of movements where they supinate, extend, pronate, extend their digits, grasp, pull back. And so we want to look at what exactly is changing in these sub-movements as the rats become impaired. And one of the things that Alex noticed, being the very observant and careful scientist that she is that the stimulated rats actually looked a lot like the control rats. Everything just seemed to be happening faster. So instead of waiting until they had their paw out over the pellet to actually execute the grasp, it's like they did everything a control rat does, they just did it sooner. And so if we look at freeze frame, so I'm going to look at as the paw extends out here on the left, and in the center, this right column here, you see the paw from the direct view. You can see this extension, pronation, digits extending here. And after 10 days, you see the same pattern. So what I'm showing is video frames matched for how far the paw is extended. If you look carefully, you can see that on the right side, which is the side that's been stimulated for 10 days, the paw is more pronated and the digits are extending sooner than they are on the left side. That's probably most evident in these frames down here at the bottom. So this is one reach, one example, but it turns out that this is really kind of shockingly robustly true across the rats. So what I'm showing here is aperture. So that's the spread of the first and the fourth digit as the rat is extending its paw. On the right, or on the horizontal axis, is the paw advancing. So the left side is paw in the chamber. The right side is the paw extending out past the pellet. And 0 is sort of arbitrarily set as the pellet. The darker colors are the later session. So what you see is that the more the stimulation happens, the rats start opening up their paws earlier and earlier in the reach. And then when you turn the stimulation off, represented in the grays, they go back to the other way. So they start opening up their paws later and later. And if you do the opposite experiment, so you turn off dopamine neurons, you actually get the opposite effect in that the paws start opening up later and later during the reach. Although the success rate for the dopamine inhibition rats actually was almost perfectly stable, which really surprised us. And the same is true if you look at the way the paw pronates. So the paw pronates earlier and earlier when you stimulate, and it pronates a little later when you inhibit dopamine neurons. One of the things kind of interesting, we hadn't really thought about this before we saw this result. When we went back and looked at the human literature, there's actually human literature on Parkinson's and reach to grasp, where Parkinson's patients shape their hands to the target later in their reach than control subjects.
Dan, can you go back, Dan? Why are the baselines so different when you compare the arch with the stimulation experiment?
I mean, they're a little different. So this is what, 60 degrees. This is 70 degrees for the black. But otherwise, the baseline should be, I feel like that's within sort of our margin of error for the baseline. All right, so the upshot of these experiments, so dopamine stimulation, first of all, it gradually worsened skilled reaching, so that fits with our learning model. And the coordination changed. So as the forelimb advanced, the paw was either opening earlier or opening later, depending on the dopamine status. And so we thought about this for a while because we really thought that the rats would reach bigger and faster and perhaps more frequently or aggressively when we did the dopamine neuron stimulation. What we think is happening is that there are these sub-movements that the rat transitions through. Now, whether they're actually discrete sub-movements or just sort of a continuum, I'm not sure how that's represented in the brain, but we interpreted that as, you know, thinking in a vigor context that dopamine is causing these transitions to happen either faster or slower. And again, the performance depends on striatal dopamine levels, but it's striatal dopamine levels when you're doing the skill. Right. So next question, we looked at our first set of results, just sort of the aggregate results, where we did dopamine neuron stimulation and the rats' reaches got progressively shorter. And then when we turned off the laser, they got progressively longer, but they really jumped back pretty quickly. They didn't seem to need this gradual decline again, or this gradual progression to get back up. So Alex designed sort of a clever way to test this, is within a single session, she would just turn the laser off and on every 5 trials. So the idea is that if they have to relearn this aberrant way of reaching every single time, then this transition from off to on should look pretty smooth. And if not, it should look very step functiony. So this is a rat that learned the task well and then got repeated stimulation. So on reach 16, if you look in the mirror view especially, you see it's starting to reach a little shorter. By the time your 70 reaches in, it barely gets its paw out of the reaching slot. So this all happened over a fairly extended period of time, probably about 2 days of training. So when Alex did this 5 on, 5 off block, so this is a laser off trial. The rat's fine. This is the next trial with the laser on. And so now the rat's severely impaired within 1 trial. And we can quantify that across rats. This is how far the rat extended its paw. This is for a single rat. And you see when the laser transitions from off, when we transition from stimulating to not stimulating, this bounces back and forth really remarkably quickly. And it's true across all the rats. So that sort of brings us back to this fuel tank model. So if learning is one side of the coin, once something's been learned in a particular off or on dopamine state, you can switch back and forth between those 2 states pretty quickly, which may in part explain why Parkinson's patients initially need a week or 2 to see how their levodopa is going to affect them. And when they stop their levodopa, often take a week or 2 to fully wear off. And then later in the disease, you give levodopa and their response correlates very strongly with plasma levels. And then they wear off and then you give them a new dose of levodopa. And what I want to emphasize is that this is in totally otherwise healthy rats. So there's nothing else going on. There isn't some chronic long-term degeneration, changes in synaptic plasticity related to loss of dopamine neurons. Well, certainly there's something going on with the circuits related to the repetitive dopamine neuron stimulation, but we don't need to invoke any changes related to the neurodegeneration itself in order to have this happen. So these are some videos I added this morning. So this is a rat getting dopamine neuron stimulation. This is day 1. So this is actually a between reach rat. And the point I want to make here is when the laser comes on, this rat looks pretty normal. It just does its thing. By day 10, when it goes to reach, that's going to trigger the laser. Now the rat's really impaired. And this happens gradually across sessions. It looks very much like levodopa-induced dyskinesias in a rat or mouse model. And again, these are totally otherwise healthy rats, so we did not have to induce neurodegeneration to get these abnormal movements. The other thing that's interesting about this is that this is the same rat getting dopamine neuron stimulation while it's reaching after the video I just showed you. And it's pretty okay reaching. So it can be spinning around, twisting, waving its limbs when it's getting dopamine neuron stimulation when it's not engaged in the task. But once it engages in the task, it actually does pretty well. This is also true of Parkinson's patients, that even patients with dyskinesias that look like they should really, really interfere with daily life, patients often can write, eat, cook, do the things they need to do. And this is just another video making the same point. This is that top view. But now the rat's going to get the laser when it's engaged in the task, and it's just totally fine. This is after it's already had that session where it was really, really impaired every time the stimulation came on. In fact, on the next reach, or the next trial, so the rat gets impaired, it has these abnormal movements. But once it decides it wants to go reach, it's fine. For the most part. So the upshot of all of this is that dopamine clearly has something to do with what I'm going to call fine motor control. That is coordination across both proximal and distal joints, regulating how something like a skilled reach is performed. And then the other surprising thing that we found is that once we've done these dopamine manipulations, you can bring back the aberrant kinematics with a single trial. And what that suggests to me, at least, is that the right way to move is still in there in a Parkinson's brain. The question is, how do you get at it? So as Martin pointed out, we sort of hammered the dopamine system here. So in some sense, it's proof of principle that this works. Does this happen under physiologic conditions in a healthy animal? And I don't know. So we started to try to sort that out. So this is work with Christian Burgess's lab. So he's been developing a skilled reaching task for mice, and we're using D-Light, which is this optical sensor for dopamine. So it's a green fluorescent protein coupled to a dopamine receptor. When dopamine binds the dopamine receptor, it changes the conformation of the GFP, and the GFP fluoresces. So when it glows green, that means dopamine's present. So Chris Phillips is a technician in Christian's lab. This is the task that Chris developed. And so in this case, there's a rotating disc, brings the pellet up, and the two horns on this mouse are optical fibers that are bringing the photometry signal out from both hemispheres. So one of the first things that Chris noticed is that there is, in fact, a transient dopamine peak when mice perform this task. So each heat map here, each line is one trial. Brighter colors, hotter colors mean more dopamine. And as we go from top to bottom, we're going from the first few trials that the mouse performed to the last trials that the mouse performed. This is across many test sessions. And what you can see is that there's a dopamine peak even very early when the mice do this, but as the mouse gets better and better at it, that peak tightens up, that peak moves earlier. And time zero here is the moment the pellet is grasped. So right around the time the mouse is grasping the pellet, there's a peak in striatal dopamine signaling. And they've done several experiments now, some in ventral striatum, some in dorsal striatum. And in dorsal striatum especially, there's this really tight peak that seems to be really very well aligned to when the mouse grasps the pellet. And they looked across learning. So the orange is dorsal striatal recordings, the bottom is ventral striatal recordings. The top row in each case is early trials, the bottom row is late trials. And so as the pellet is grasped and consumed, there's a big signal in dorsal striatum. There's a similar signal in ventral striatum. What's really clear in the ventral striatum is that by the time you get to the last 10 trials, right around here, this is when the disc starts to rotate to bring the next pellet into view, is you start to see a dopamine peak that wasn't present on the first 10 trials. Very much like that.
It doesn't look exactly like a prediction error, doesn't it?
It does or does not?
Does not.
No, it does not, but it's shifting. I mean, it's shifting earlier. And yeah, so earlier when I said, I sort of hedged on, this is sort of the basic idea. I hedged on it because we do also see these dopamine transients just related to movement itself that shouldn't have anything to do with an RPE signal. But it's certainly reminiscent of this migration from the unconditioned to the conditioned stimulus. And that as the mouse gets better and better at this task, it becomes more confident that it's probably going to get the sugar pellet when it rotates in front of it. You see the signal migrating. So what does this have to do with Parkinson's? This is a figure from a review, actually not a review, it's sort of a summary figure from a paper from Paul Garris's lab. And the argument that they're making is that striatal dopamine levels generally don't go down early in Parkinson's. You have to lose a lot of dopamine neurons before the fuel tank the needle on the fuel tank really starts to head down. And the reason for that, they argue, and there's pretty good evidence from their lab for this, is that not only are you losing the terminals that release dopamine in Parkinson's disease, but you're also losing the terminals that recycle the dopamine. So the dopamine gets released, it diffuses out, these dotted terminals are no longer there to serve, to pick the dopamine back up, and you wind up with actually what they term passive stabilization of striatal dopamine levels as dopamine terminals are lost. But what you do lose is you lose the capacity to tightly regulate this phasic signaling. That when you suddenly increase firing, that dopamine is not going to get taken up quickly, and it's going to diffuse out, and there's nothing in other places to take it up. So phasic signaling is probably lost fairly early in Parkinson's, and it's probably not restored by levodopa. I am unaware of anyone being able to directly make this measurement to date, but there's no reason to think that just giving more substrate would bring back the phasic signaling. And so our hypothesis that we are working on trying to test now is that it's this loss of phasic signaling that impairs dexterity, because you can't get that brief reward signal saying you did that last reach right. That will gradually impair it, and it won't be restored by levodopa because levodopa doesn't restore phasic signaling. All right, so that is what I have. These are the big points. Certainly dopamine makes people move bigger and faster, especially if they have Parkinson's disease and they get levodopa. But it also does have something to do with regulating coordination, and that probably is linked to phasic dopamine release, time to these types of movements. Whether that's a reward prediction error signal has something to do with directly regulating the movement itself. I'm not entirely sure, and at this point I would say that it's a nice idea, but yet to be proven. It's plausible that reinforcement learning models are the link between the vigor and coordination roles for dopamine. And this, I think, is one of the more, at least at first, was one of our more surprising findings, is that Once abnormal movements are gradually acquired in the setting of altered dopamine signaling, they come back immediately, which is very reminiscent of motor fluctuations and dyskinesias in actual Parkinson's patients. And we do know that there are transient striatal dopamine peaks as mice perform this movement. What exactly they mean is things that we're working on. So getting back to my original question, why is manual dexterity impaired in Parkinson's? Was certainly tremor and bradykinesia don't help. But there seems to be something else in addition to just moving slowly or just having tremor. And we believe that that's related to this loss of phasic signaling, and we're working to try and improve that definitively. And these are all things that I've already said. Yeah. With that, I finish up. Thank all the people that did the work, especially Alex and Damien. And with that, I'll take questions.
Okay. All right, very good. So questions for Dan? So Dan, just let me ask a question. So I think, but you're arguing there's a vigor component of this because of the more rapid transition across the sub movements.
Right.
But I think, as you know, I mean, we published on this. We also think there's a vigor component related to tonic signaling, which, may be the thing that potentially that levodopa partially restores, at least for chronic treatment. Do you think, so that would mean that the, vigor, again, it's, as you said, it's a broad concept, and maybe there's actually different forms of vigor, or some you'd have to decompose it into different components potentially?
Yeah, I mean, so for one thing, even though we're doing semi-timed dopamine manipulations, they're still several seconds long. Mm-hmm. So certainly longer than what you consider a natural phasic dopamine signal.
Right.
So it may be that there's a tonic-like signal in those 5-second stimulation runs. I think the other thing is that it's really hard to separate things out in humans with Parkinson's because they've been denervated for a while by the time they're diagnosed. And even at diagnosis, I don't know. I mean, I feel like there's a reasonable chance that they're still pretty close to normal tonic dopamine levels. I don't know, other than, I don't know of anyone being able to make a direct measurement at diagnosis in humans. Even PET imaging is, changes.
Okay. Well, I don't think there's anyone who's made a direct measurement of, certainly no one, I don't think, has made a direct measurement of how much dopamine there is in the striatum in a newly diagnosed PD patient. However, there may be a relevant PET observation that was made, actually post-mortem and PET observation was made quite a while ago, which is that in de novo patients, there is actually upregulation of D2 receptors. And, that plausibly, again, this requires assumptions, that plausibly could be attributed to deficient signaling, dopamine signaling. So, resulting in either actual overexpression or more translocation of receptors to the plasma membrane. So I think that, at least that happens in the dorsal putamen. That would suggest there actually is perhaps an extracellular deficiency at diagnosis.
Right. Well, I think that would be the sort of the obvious hypothesis, is that you become symptomatic once the buffering capacity is gone.
Right.
Once the tonic levels start to go down, that's when people come to medical attention.
Right.
Yeah. So I think, though, that this issue of dopamine and vigor, I think it gets masked by the fact that once you start giving people levodopa, you're already in this sort of going up and going down mode.
Down phase, right.
And so, I mean, I think, I think most patients, they take their first levodopa pill and they don't say, wow, this is amazing an hour later, right? They take their levodopa for a week or two and they're, wow, I'm doing pretty well. And so I think that's probably analogous to what we're seeing, in that, the first few times you bring the dopamine levels back up to normal, there's like, but once you get there, then you start to go up and down more quickly. And then you start to see vigor effects, what look like vigor effects of going back up and back down because the transitions happen more quickly.
Okay.
Like, I wonder actually, like, if you took the very first levodopa dose of a Parkinson's patient, would you see something on an assay of vigor?
I might be able to tell you that I think Jay Nutt would have some data on that, because he's done some of those experiments.
Oh, yeah. So they did the IV infusions, right?
Right.
But even they saw a much bigger effect after multiple infusions, I think.
Yeah, I'd have to go back and look. Yeah.
Good point.
Yeah.
Then in your fiber photometry experiments, do you actually see any evidence that what you call tonic alterations in dopamine levels, that this thing really exists, for example, prior to engaging into the session versus during the session? So if you ignore the transients, do you see any evidence that this tonic thing really exists, or is this just, as is the case probably in my view, just a little bit of our, old style traditional thinking?
So are you asking, do I think that
do you see in your fiber photometry experiments, do you see any evidence that tonic alterations exist, and if so, on what time scale might those be?
Oh yeah, so have not looked on that kind of time scale, and I think there are issues related to baselines drifting with the photometry. So it's not the best technique for measuring absolute levels of dopamine, but it's a good technique for measuring changes in levels of dopamine. So so the short answer is I don't know, and I don't think that's the right technique to try and answer that question. I did send a proposal to the VA that they didn't especially care for. That where we were going to try to do the photometry and we were going to do microdialysis with Bob Kennedy, and try and look at exactly that, like what, how are these things linked to each other, and if you do partial dopamine lesions, when does one go down versus the other going down, and those sorts of things.
Yeah, but you could simply look at within session versus outside session and see whether averages over tens of seconds or so really start to differ in a systematic fashion, and you can exclude that you just have technical baseline drifts. I mean, I would put my money on the probably exotic possibility that the tonic component just doesn't exist. It's just one of those old mares that doesn't go away thanks to old style techniques, but that's just for fun.
Well, so I guess when you say that the tonic dopamine doesn't exist, do you mean that it's not a distinct thing from phasic release, or, there's dopamine in the striatum, right?
Yes, but all there is phasic.
Okay.
Right, sure.
Yeah.
I guess I'm not following the distinction you're making.
Another time.
Well, I think, okay. Well, that would be worth discussion another time, because I think my inclination would be to disagree with Martin about this, actually. So yeah.
So Josh's argument in Arif Hamid's paper was that there's no such thing as tonic and phasic dopamine. There's just dopamine release. And if dopamine neurons change their activity quickly, it looks like phasic dopamine. And if they change their activity slowly or just fire at the same rate, it looks like tonic. But
you can define it, basically as you did in your experiment, right? Is it strictly evoked, right? And is that all there is to it by whatever the animal is doing, like in your task? Or are there fluctuations happening outside the
like behavior modulated fluctuations that raise or lower the tonic dopamine levels? Yeah.
Right.
Okay.
Right.
All right.
Right. Right. Well, I will say, I think in terms of normal function, I think Martin's point would be correct, but I think that the differences in the PD situation, I think that would be there. I think you're outside the range of the normal physiological range, and that may be, I don't think those two would necessarily be exactly comparable. So, okay. Any other questions for Dan or? Okay. Well, thanks, Dan. Thanks very much for a really nice talk. That was a lot of fun. I think, we're going to have a Udall Center Executive Committee now, which we could start now. So those of you who are not on the executive committee, you can just pop out and then